And we have now our next talk, which is about translating things from the B method into SMT.
Right, so first, thank you, Matthias and Sophie, for the invitation. So my name is Vincent. I'm a second year PhD student at the University of Lorraine at Nancy. Actually, I'm starting my third year now. And today I'm going to talk about encoding the B language into the SMT-LIB language. So we'll spend the next hour together, so please don't hesitate to interrupt me during the talk if you have any question. So my talk is split into two parts. The first three sections are more about the encoding itself from the implementation point of view, and the three next parts are more about the formalization of the languages and the proofs and so on. So first, for those of you who don't know the B method, so we often start from a physical system that we want to specify. So we want to assert some formulas, logical formulas on those systems in order to verify some properties. So it might be liveness properties, it might be some behaviors that we want to check or to ensure. This physical system, so we specify it into what we call a B component or a B machine, using the B language. So it's a mathematical specification language. It's not really programming language, but it can be refined into one. Now from this B component, we generate what we call proof obligations. So those are logical formulas that are sufficient to ensure that the behaviors that we want to check are actually correct. And we have a tool that does that is called the proof obligation generator. And it provides us a POG file. So it's roughly an XML file gathering all the proof obligations. So it's B terms, but in XML format. And now as a user, we have several choices. We can either discharge the proof obligations by hand using some tactics in Atelier B or Rodin. So just as we read on paper, we can also call internal solvers, such as the predicate prover from Atelier B, which is the historical one. Or if none of those methods work, we can also call external solvers, such as SMT solvers. But in order to be able to do that, we first need to translate a PG file into an SMT-LIB file. And so there is a tool that also does that, which is called pptrans-SMT. And this is the tool that is actually used in Atelier B and Rodin, for example. And it performs the transformation. And now from the SMT-LIB file, we can run just either solver, so CBC5, Verity, Z3, and really hope for an answer, so sat, unsat, or unknown, if it doesn't. Right, so just a quick reminder on the SMT-LIB language. So it's the standard input format for SMT solvers. Up to version 2.6, it was based on many sorted first-order logic. And what is cool with SMT-LIB is that it comes with many theories that are then up to the solver to implement the different solving methods. But last year was released version 2.7, which brings higher order constructs and higher order types. So we now have access to lambda abstractions and the arrow type constructor. And this opens the door to higher order logic in SMT solvers. Yet it's only supported by CVC5, but it's already enough to test some things out. Right, so let's come back to this graphic. So for my PhD, I'm focusing on this part, the pptrans-SMT part. And since now we have access to a whole new set of formulas, and I decided to start from scratch and design my own encoder for the B proof obligations. And I called it the B proof encoder. So the B encoder, sorry. And it's called beer. And for my master's degree, so I spent a year in Munich. And one thing that Germany taught me is to lean on beer. And so I wrote beer in lean. So for those of you who don't know Lean, it's a very powerful proof programming language that is also a proof assistant, and it supports higher order logic and dependent types. It's really powerful, and what I really hope is to be able to prove correctness of my encoding. So its architecture is as follows. As I said, I'm taking a PNG file as input. Then I parse it into a Lean representation of the B language. Then I encode it into SMT-LIB. So this is actually the big part. And then I can write it out into an SMT-LIB file. So I have to put an SMT-LIB file. Now, on top of that, as I said, I really want to perform some proofs and to check that my encoding is correct. So on top of this lower level representation, I have an abstract representation of both languages. So first, I will talk about it later. And so those languages are meant to be more abstract, and I want to interpret those languages into another theory to be able to state some properties about them. So now I had a choice on which theory I could choose in order to do that. And I could choose Lean formal logic theory, but I chose to interpret that into ZFC set theory because the B language is really close to ZFC set theory, actually. For SMT-LIB, well, it's a bit trickier, but yeah, I will talk about this also. And so this is the general architecture of the tool. And what is really cool in Lean is that we really have the program on the one hand and the proofs on the other hand, and they are independent, but still work together. And at compile time, the proofs are just erased. And that's also why I have two representations, a more concrete one for the program and a more abstract one for the proofs. And so the program is more efficient than if I was using, for example, more abstract data structures. Right, so I'm going to talk a little bit about the encoding itself, the differences between the former one and the new one. So as I said, the biggest difference is that mine uses higher order logic, of course. The first consequence that it has is that in PP-Trans SMT, the sets were only specified. They didn't have a proper definition, they were only specified. And in order to do this, we used an uninterpreted predicate membership, so which was an axiomatized symbol, and two abstract sorts, P and C. So P is unary, and it's meant to represent the power set, and C is binary and is meant to represent the Cartesian product. But it's only an intuition, and there are no axioms on these sorts. In my encoding, with higher order logic, I'm able to encode sets, so via the characteristic predicate of the set, but I'm able to give it a proper definition. So just to give an example, if we have this enumerated set with 3 elements, E1 to 3, in PP-Trans SMT, we would have the following encoding. So first we have the two abstract sorts, P and C. Then we have a constant S that types into P of int, but we have to understand that it means power set of int, because in B, the enumerations are always non-empty and countable, so we can just cast them into the integers. Then we have 3 constants, E1 to 3, that are all different. And we have to declare a membership function. So again, it's only a declaration. There is absolutely no axiom on this function. And then we finally add the specification for what does it mean to be a member of S? Well, it means being either equal to E1 to 3. Okay, so this specification actually specifies both membership and the property of belonging to S. So we actually specify 2 different things. And being a member of S is not, I mean, it's a theorem to prove, right? We have to instantiate a quantifier and so on. in my encoding, so the beginning is the same, I have 3 constants that are all different, but then I just define S as a lambda term, right? So notice the arrow type from int to bool. And now S is really equal to this lambda. Now, if we want to encode that X is a member of S, well, we just apply S to this X. And now checking that X is a member of S, it's just a simple beta reduction, right? It's not a theorem to prove. But the definition then is the same. Okay, so this is what I said. Only expressions like X is a member of S are encoded, whereas in my encoding, sets alone make sense, and X is a member of S is true by definition or by beta reduction, but it's almost true by definition or false by definition. And finally, the last difference between both encodings is that in PP-trans SMT, functions are mathematical functions. So they're functional relations, just as they are in ZFC set theory. Whereas in my encoding, I tried to encode functions as functions, but programming language functions when I can, so sometimes. Again, an example of this, suppose we have a function f, a partial function from A to B, set A to set B, so this is the B notation. In PP-trans SMT, the function is seen as a functional relation, so it's a subset of A times B that has the property of being functional. So if f of x is equal to y and f of x is equal to z, then y has to be equal to z. Now, a common way to encode partial functions in programming languages is to see them as total functions to which we add an element in the codomain. So in category theory, we could say we augment the codomain with a bottom, but it's just adding an element that catches the undefined part of the domain, right? So pretty simple. And this is actually what I did in SMT-LIB. So I declared a parametric data type option that is either a sum of something or a sum. And this is really the definition that I used in the encoding. So the option type is used in many programming languages. In Haskell, it's the maybe type. And this is going to help me define partial functions. But notice that there are going to be true functions, like in the programming language sense. So let's come back to this example with the F. We just represent tau A and tau B, the types of A and B. So in PP-trans SMT, this would be the encoding that declares F. So as I said, F is a subset of the Cartesian product of A and B. Then we declare a new membership predicate that now takes 3 elements, so the X, the Y, and the F. And X is a member of, mem0 X, Y, F means that F of X is equal to Y. It's a bit complicated, but it's what it means. And then we specify that the relation F is functional. Well, all of this is related to the fact that F is a function. So if we directly embed all of that into the type of F, what we get in beer, so in my encoding, is simply this. And this is telling just the same, right? But now we are using this arrow type. And it really means that it goes from tau A to option tau B, so it's a partial function from tau A to tau B. Notice that still in both cases, we have to specify the domain of F, it's a subset of A, and so on. But we have to do this in both cases. Right, the question is, how large is the gain? Which gain? Well, SMT solvers really don't like quantified variables because they have to instantiate them. And a good example of this is the finite predicate B, which is defined as follows. It says that a set S is finite if we can find a total injective function from the set to some interval of integers. So we can actually count elements in the set. If we unfold everything, we have this. And we have like a dozen quantified variables. And this says that S is finite. Now, again, if we are able to embed the fact, so notice the notations here are, it's not B, it's not SMT-LIB, it's bit, so it's B with type annotations, but whatever. If we embed the fact that f is a function in this, we get something like that. And now we divided the number of quantified variables by 2. So it seems to be significant. Question is, does that work? Well, let's consider a simple, really simple B machine. So by the way, this is how we write B machines. So we have a variable as 0. We initialize it to a member of the power set of NAT. So NAT is the set of finite machine natural numbers. So between 0 and 2 to the power something. And we check the following invariant. S0 is a subset of NAT, and S0 intersected with the negative integers is finite. Right? Pretty simple. The following proof obligation is generated, so it's just what I just said. So S0 is in the power set of NAT, implies S0 is a subset of NAT, and S0 intersected with the negative integers is finite. Okay. The first part, this part is trivial by definition of being a member of the power set. We are a subset. And the second part, well, the negative integers, this is an infinite set. So it just boils down to proving that S0 is a member of power set of NAT, implies S0 is finite. But this is true because S0 is a subset of a finite set, so it's finite. So it seems to be quite trivial to prove. Still, the predicate prover from Atelier B fails to prove it. CVC5 with PP trans SMT fails to prove it, but CVC5 with beer successfully discharges the proof obligation. So it seems to work, right? But in order to make sure that it works, we would need to test it against many proof obligations to make benchmarks. So this is what I did. And actually, we have a public data set of proof obligations with nearly 700,000 proof obligations that are from the industrial world, so real world proof obligations. Some of them are like millions of lines of POG. And it's often trivial proof obligations, but really, really large. With the current subset of the language that I'm supporting, I'm able to encode a bit more than 15,000 proof obligations. First thing to notice is that, so it's PP trans against beer. In 95% of the cases, we agree, both agree. Now, there are some cases in which we don't. First, so in 200 cases, I'm able to discharge the proof obligation, whereas PP trans is not able to discharge it. By taking a look to those proof obligations, I noticed that it's often proof obligations that are related to higher order things. And this is how I designed the encoder. And so I'm pretty happy because this shows that in the higher order cases, I'm able to actually have some gain. Now, this is a bit more concerning because it means that PP trans is able to solve like twice as many proof obligations that I'm not able to encode. And in those cases, it's often the case that the proof obligations is really simple, but the overhead I'm adding with encoding functions as function, just like this makes the solver struggle and it times out. And now there are still cases in which both encoder just time out, and it's often related to the fact that the proof obligations are, as I said, are really, really big, and just reading the proof obligation makes the solver time out. Now there is this unset set. So this is actually a bug in PP trans because the proof obligation is completely valid, and the counter model found by Beer is also completely valid. So like, and then there are, so this case here, set, the proof obligation is actually not valid. And both encoders are able to show that. And those 5 here and here, I don't really know. Like, they are so huge, I can't really decide if the proof application is really not valid or if it's a bug. By the way, if I'm able to prove that my encoder is correct, I will know that this actually means that the proof application is invalid. Right. So this is the end of the first part related to the implementation. You can take 2 minutes break for questions at this point if you want.
Yeah. So this is interesting. When we worked on this transformation from B to SMT with David a very long time ago, we also tried to encode directly functions as functions and using predicates. We didn't have higher order, right?
Yeah.
And well, it made things less efficient in working with proof obligations. So it's kind of interesting that you kind of get to the same conclusion, but less so, right? So it seems that it has, that's HO is actually working, right?
Yeah, and so I didn't say it, but I had, and we actually have to enable MBQI, or I mean, just any kind of instantiation, but setting the logic of the solver to this HO all, we have to use instantiation, and it seems to be working pretty well. It's just timing out pretty quickly, but it's not surprising. And another conclusion of those results is that I'm not trying to compete with PP-Trans SMT. I'm just trying to complete it. And I think we have to keep it because for simple problems, as you see, I'm just adding so much overhead and interpreting things in higher order in general and things like that, whereas maybe it's just a SAT problem. And so making the solver timeout on such problems is pretty surprising, but so the approach with portfolio solver, I think we have to keep it. And it's just how, for example, Sledgehammer in Isabelle works. It just tries to encode one problem with several encodings, and now on each encoding, it runs several solvers and just hope to have one answer at least.
Well, my understanding of this table is also that SMT solvers have not tuned much for higher order proof obligations, but it's a necessary step forward. So you need to go to one stage where it's less efficient, and then we will work on HRO, SMT, and then you will get the benefits in beer.
If you go backward to the star, converting the partial functions, the undefined functions into total functions.
This slide?
I think it was backward one. Yes, here. So this trick, this new high order encoding. So in 78, I was a master student in logic in Sofia under the work of Dimitar Skordev. He had just published with a very famous book, Combinatorial Spaces, for all the results of recursion theory. And he gave me this task. Try to see what you can do with the partial functions. And that's what I did. This star, you introduce special symbol. This is a general trick nowadays, but in those years it was not. So theoretically, I managed somehow in a mysterious way. I focused on it, and I proved that this trick is a wonderful one theoretically. So actually, when you introduce this, all those partial, all the results, the two major results for recursion theory, theorem 1 and theorem 2 for the minimal fixed points, they apply. So it's a wonderful machinery, and I'll show that too. I use it, but genuinely, you still have this Turing problem. If there is some point where it's not defined and everything is defined after that point, it cannot be reached. But theoretically, it's wonderful if you know.
So in the case of proof obligations, it's not really a problem because we are never calling functions. So we have no recursive functions. Those are only symbols, and it's just for the typing that we need those partial functions. It's just because B has support for partial and total functions. And so we have to represent it one way or another. But yeah, it's
I'll try to show an example, two baby examples, maybe at least one. Today for 30 minutes. But this is a very good trick. And theoretically it is good.
Right, so let's carry on. So now I'm changing completely. We are talking now about formal things and how to formalize the B language, the SMT language, how I'm going to type them, and in the end, I want to give a proper semantics to both languages in order to be able to prove things onto the encoder. So let's start with the syntax. So we are going this way now. So I presented just the top layer. Now we are going to dive into the abstractions. And this is the roadmap. So syntax, type system, and semantics. Right, so as I said, I have two different representations for my syntax. I have a concrete one, which is lower level and meant to be more efficient at runtime. And it uses so lower level constructs. And this is the grammar I'm using. This is the concrete syntax of the B language. So I'm only showing things for the B language. I did similar things for the SMT-LIB language, but I don't have time to show both languages. Right, so I have the variables are strings, I have integers, booleans, pairs, arithmetics, logic symbols, set operations, function symbols, and so on. So I have three kinds of binders for all set comprehension and lambda. They all have the same type, list of string, term to term. So they are bounded binders because they all take a limit, right? All right, and this is a deep embedding of the language, and I represent strings, variables with strings. Right, so as an example, those four terms are all syntactically valid. They can actually be constructed, right? Even this one, lambda nothing is in int2, such that var x is equal to 0 and set of booleans. It's syntactically valid. Some of those terms are type correct. Some of those terms are said to be well formed, right? So for example, cardinal of Z is a member of Z is not said to be well formed, right? Because cardinals of Z is not well formed. And first one, it just does not make any sense, right? But this is what we are trying to formalize. So type system and an idea of meaning, so it's semantics. Right, so on top of that, we define an abstraction of those terms. The idea is to ease formal reasoning, to bring higher level constructions, right? So for example, for the binders, I'm using lists, right? So this is too low level. And also the most important thing is that I want to bridge the gap between this deep representation and I want to relate it with the underlying system. So here it's lean. And just an example of this, in this term, for all x in D such that P, here P is only a term, right? It's not really a predicate. It's just a term from the language. And this x here has no relation with P. P is not binding anything, right? So because it's a deep representation. The consequence of that is that we have to deal with alpha renaming and substitutions by hand, right? We have to handle that explicitly. For example, the identity function on Z has infinitely many representations. And for example, in this lambda x plus y, if we want to substitute y for x, well, what should I do? Should I first rename this x or just replace the y by x? So those are questions that are related to deep embeddings. And this is something I don't want to deal with. So I will delegate variable management to the underlying formal system. So this trick is called, or is linked to switching for a representation that is called a FOS. So it's a parametric higher order abstract syntax. And the idea is the following. So this is the general type, as I said, of my bounded binaries that I had before. So list of strings, term to term, and it returns a term. The idea of delegating variable management to Lean is to say, well, I don't want to take explicitly the variables as arguments. I want to put it there. And so this is the P, this is the motive, the predicate, which, by the way, becomes a real motive now, a real predicate. So as I said, I want to make it parametric as well. So instead of string, I want something slightly more generic. So I make an explicit dependency on the type V for variables. And the last trick is I don't want to deal with nested induction in Lean. So I just switch from lists to functions, n-ary functions. And this n here is made implicit. And the idea is n is the number of variables that are going to be bound by the binary. Right, just an example of this. Here is a concrete term for all x, y, and z times z, for x is equal to y. The abstract representation of this would be for all, no dependency on any variables, z times z, and then I have to provide a motive. So fun xy for x is equal to y. But the big difference is that this fun here, we are binding variables from Lean directly. There is no, because here I could say, I could replace x with Vincent and not change this x here. There is absolutely no relation between those variables here and here, rather than this x here being explicitly this x here. Right. Of course, we have an abstraction function that maps concrete terms to abstract terms, right? The intuition is that it's almost the identity function, because we just want to be able to say, okay, I have a concrete term, and then I can abstract this term up to a renaming context. Well, in fact, the implementation is a little more complex, but I'm not showing it for now. And this is just a notation. This is how I denote T being extracted under delta. And delta renames variables, so concrete variables to abstract. Okay, just an example of the abstraction. So consider this term for all x and z var x is equal to var y. Y is a free variable here, so we have to take it into the renaming context delta and rename it to capital Y, which is an element of the set of abstract variables. So what is the abstraction of this term? Well, we just recursively call the abstraction on subterms. So it's equal to the abstraction on Z of something. We have to bind a new variable for X, but Lean has to bind a new variable, not us. And then we just call recursively on this var X is equal to var Y, abstracted on the delta, in which we add the variable that we are binding. And we get this. And this is the abstract version of this concrete type. Yeah, in the actual implementation, as I said, it's a bit more, we have to require that delta contains at least all three variables. So imagine here, if we don't have delta, in delta, if we don't have Y, well, how am I supposed to rename the Y here? I can't. All right, so we can check the first box. Syntax is done. Now we have to define a type system. So properly speaking, B is untyped, but I chose to on top of that, define a type system in order to verify some typing properties, because even though it's untyped, in POG files, there is an attribute that is called the type ref, but whatever, that is gathering some typing information. So this is something I also want to check at runtime. So the type system is really, really basic. We have integers, Boolean, set, and product. We can transform those types into terms if needed, because as I said in B, they are speaking of types, but it's not types. So each time the B people are talking about types, it's actually terms. So int is Z, bool is B, set is parset, and product is Cartesian. Very simple. Since we have types, we need typing contexts. Again, I have two representations, abstract one and a concrete one. So the concrete one is meant to be efficient at runtime. So here I chose A list, so but whatever, so it's specific to Lean. The difference between association lists and A list is that I have unicity ensured under the keys, whatever. So it maps strings to B types. And in the abstract world, well, I want something higher order, right? I want something easy to manipulate within the proofs. So it's just a map, V to object B type. And this is really easy to work with. Plus, I don't need all auxiliary theorems that I would have, for example, on A list. First, they not always exist. And you have to really, when you work with A list or any concrete data structure in Lean, you need plenty of theorems to show that what you do is correct. Whereas on maps, I mean, it's just a function. I don't need any theorem to prove that. If I add an element in the map, I get this or that. You just get it by construction. I have also an abstraction function, but whatever. And now I can define what typing means. So it's an inductive predicate that is built up in terms by induction for both concrete and abstract terms. So I have two sets of rules. Of course, those rules are different for the rules involving variables because they rely on the data structure. So for example, for the variable rule, well, the method allowing me to take a look to what is in gamma is called lookup. Whereas in the abstract world, I'm just evaluating things on my abstract data structures. Really easy. The rules not involving variables are all identical, of course. So just an example with maplet and membership, and actually all the other rules that do not involve variables. With binders, it's a bit more tedious. So I'm just showing the rule for lambda, the lambda binder, and it's actually quite similar for the set comprehension and for all. And here is the concrete lambda type. So what do we need? First, we need to define the number of variables that we are going to bind, which is a positive number. We cannot bind 0 variable. So not like the example where I was binding 0 variable. Now, typing enforces the fact that you have to bind at least 1 variable. We need gamma, concrete type context. We need a family of concrete variables, a family of types, a return type, a family of domains, because my binders are bounded, and a term f, that is the function in the lambda. What are the assumptions in order to prove, so to define, but actually to prove this? So that gamma times the lambda v1 to vn is in d1 times dn, such that f with the type. So again, this is the type of functional relation. So it's a set alpha1 times blah, 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 times alpha n times psi. What are the assumptions for this? Well, first, the vi should be fresh, so not be already in gamma. All the domains should have the proper type, so the pairwise, they are pairwise in the corresponding type. So the idea is VI will have type alpha I, but VI has to be in the domain DI, so DI has to have type Z alpha I, right? This is what it's telling. And gamma, in which we add all the VI alpha I, should type F with type psi. So notice this is for lambda. In the case of a for all, this would be Boolean. And also in the case of set comprehension. And the type here would be adapted as well. Right, so this is the rule for concrete lambda. Now for abstract lambda, it's really subtle. Conclusion almost doesn't change, the syntax only changes because we have no dependency in variables. The n here doesn't change. Gamma is now an abstract type context. We have this same family alpha I and xi of B types, di of domains, and F is now an abstract motive, right? It's not just a term, it's a motive. Notice we have no dependency on any family of variables because we delegated it to B. So we don't have to explicitly require a family of variables. This assumption is the same. Di still types into set of I. And for typing F, well, now we have to quantify over any family of variables. So we say for any family of variables, this gamma updated with the VI alpha I types F taken on this family with the type psi, right? So it's the same rule as before, but just we quantified here over variables, over just any family of variables. Right. Now that we have a type system, we really want to prove things on this type system. The usual theorems that we prove on type systems are some things like weakening, all right? So we can, if we have a term that types, we can add variables in that context, the term still types correctly. On the contrary, we can remove variables that do not appear in a term and the term still types correctly. And the term has at most one type. So this is quite easy to prove actually in Lean. And this is the first thing I did when I defined the type system. Right, you can check second box. Now for the semantics. So when we define semantics for a language, we have several choices in terms of what kind of semantics. Since I want to prove what or determine what the encoding is computing, I'm not trying to take a look at how it's computing things. I went for denotational semantics because I'm computing domains. And this is also why I wanted to integrate things into ZFC set theory, because I'm working with sets. Sorry, it's more convenient to work with sets when we're speaking about domains. In order to interpret the B syntax into ZFC set theory, well, first I have to be able to manipulate ZFC set theory into Lean. So there is actually a library that does that. But so in MathLib, mathematical library of Lean, it's really lacunary, and I had to extend it. So it only provides this type ZF sets, and ZF sets are the ZFC sets, and the library, so the whole library on ZF sets is only building ZF sets, and that's all. So I first had to define Booleans and the Boolean algebra, and so natural numbers, a set of natural numbers, a proper type for natural numbers, arithmetics and theorems. Then the same thing with integers, and for rationals, I just stopped after the definition of the type, and the reals I just didn't define it, because just so from the Booleans to ZF-rat, it's approximately 5,000 lines of code, so it's already big. And for B, I just need integers, so I stopped right there. But yeah, then I had a usable theory. So I'm just defining math again in ZFC with properties and functions and so on and so on. But now it's usable. So we can start to define things. So as I said, I want to define a denotation function for atoms. And so this denotation function will take a term as input. And the question is, as output, well, we are just going to use the forwards. And so in order to, instead of returning a set, I want to return something in the type of the parameters, the parameter of the variables. So I'm returning something of type v. This might be a bit puzzling at first. So the idea is to put this. My variables will depend on ZF sets, and I'm returning a ZF set. Right? So this is maybe less puzzling. And what I'm actually doing is a bit slightly more specific. I'm doing this with a type that I called DOM, and this DOM is defined like this. Read this as in exists. So it's a triple composed of a set X, the ZF set X, a B type tau, and it provides a proof that X is a member of tau transformed into set. So for example, if tau is int, the transformation is Z, but Z in ZFC, not in B. All right, so DOM is the type for triples that respect this predicate here. Right, so it's almost returning ZF sets. And as I said, the whole purpose of the forest representation is to pour semantics into the syntax. What it means is that what is the denotation of a variable now? It's really simple. It's the variable itself. And this is what is incredible about this representation, because now remember, the type DOM is the type of triples. It's the type of triples that have this shape. So ZF set, a type, and a proof. So a proof that V is in tau. And so this allows me to also check typing, properties, and so on within the semantics. But this is all embedded into the type of variables. Right? So this is what I found to be incredible. All right, so there are some really simple cases. For example, for integers, what is the denotation of int n? Well, I just take n, I transform it into a ZF set, so a ZF int. It has the type int, and I have to provide a proof that of int n is a member of Z, which is quite easy because this is by construction of this function. Right? For Boolean, it's quite similar, just change with bool and set of booleans. And it's actually quite easy for all the binary cases, I mean, unary and binary cases, but let's just consider, for example, this, the constructor for pairs. So I'm defining the semantics by induction. So by induction, we assume that we have two terms, X and Y, two abstract terms that actually have denotations. So X is equal to X alpha and proof that X is in alpha, and same for Y. And inductively, we want to build the denotation of the pair XY. So it's built as follows. The pair XY is denoted by this triple. So the pair XY taken in ZFC. Now the encoding of pair is in ZFC. So this is called the Kuratowski pairs. It's just encoding pairs, whatever. It has type alpha times beta. And we have to provide a proof that XY is alpha times beta. When I say we have to provide a proof, I say we have to prove it. So we have to build the proof. So this, we have to build it, but it's quite easy because by definition, alpha times beta transformed into set is just alpha Cartesian product beta. But this, we can rewrite it as follows. And this is exactly what is given by the induction hypothesis. So this is quite easy to construct. And we're done. We have defined the denotation of a pair. Now binders again are a little more tedious. So now I'm only showing the case of the for all to change. The intuition is quite easy. Consider a domain that is enumerated. But the intuition is that we want to consider that the denotation of the for all is just a predicate, but taken on each element of the domain, right? This is the intuition that we want, taken conjunctively. So we really want to write it like that. So the enumerated conjunction. And by extension, we also want to write something that looks like this, right? So we really hope that the denotation of the for all is the big conjunction taken on all elements of the domain on which we evaluate the predicates. So this makes absolutely no sense here from the types point of view and so on, but let's try to formalize it a bit more properly. So again, by induction, we assume that we have a term D and a motive P, and we assume that D has a denotation. So calligraphic D, set tau, and a proof that D is in tau. By the typing, we also obtain that T is an enumerated product with n components, and this n being the same as this n here. So this means that just any variable has a proper type. Right. Now we define a function. This is the worst slide of the presentation. Now we define a function that is almost the denotation of P for any z of set Z. We define P of Z that will be equal to PZ or false, and it's equal to PZ when we are able to write Z as a tuple with n components, such that Z is in tau transformed into Z of Z. And such that when we take P, when we evaluate P over this family of variables, it has a denotation for which the first component is PZ. If this is true, we just return PZ and false otherwise, which means we just consider elements that are in the domain or that type into this type. Notice here the dashes means just this is going to be bool and a proof that PZ is in bool, but we don't need it at this point. So just put dashes. All right, we are almost done. Now we can define the denotation of the for all. So the denotation of the for all is this triple. The first component is the conjunction on all elements of the domain taken over P of X. So notice this is really, really close from the intuition on the slide before. Obviously, this has the type bool, and we have to provide a proof that the for all actually is a member of bool transformed into set. Right, this is the denotation of a for all. For lambda and set comprehension, it's not really similar, but I can't show it. We are not done yet. As I said, we have to provide the proofs. Again, this means we have to prove things, which means we have to prove this. This is not really difficult because we can write it like that. And hopefully the set of booleans is closed under conjunction. So this is easy. We also have to prove this, the little pfxi tau I. So the family we're building recursively can be built. And so we have to prove that for all z in tau, if z can be written as a tuple with n components, then every single xi is in tau I. This is an easy proof. I'm not showing it. All right, you can check the next box. And now my presentation is almost done, but you have to understand that this is just the beginning for me. I just wrote definitions at this point, and now I can start to prove things. So I'm just going to show you an example of the kind of theorems I'm proving, but I have no longer time to show you other theorems. The very first theorem that I proved in Lean is that I'm not doing things just at random. So if I have a term that types with the type tau, then the type provided by the denotation is actually the same, right? Which seems quite trivial, but it's actually not. But we can prove it using the law. So prove T sigma here. And this is why the type of my denotation is not just ZF set, but this DOM that I showed you. This is what allows me to get the type computed the same. Second theorem that I proved is upon the simplifier. So when I read a POG, I first simplify it. So for example, anything that is that has the shape 0 plus n, p and true, things like that. I simplify them. So p and true, I just simplify it down to p, for example. But this simplifier is only performing syntactic transformations on concrete terms, right? It's part of the tool beer. So it's related to the implementation. So it's taking concrete terms as input. So if I want to prove things on this simplifier, I have to abstract things up. And this is what the theorems states. So if I take T and I abstract it under delta, now if T has a denotation, then the simplified term has the same denotation. So the simplifier is not changing the semantics, which is something we hope to be true, and it actually holds. Notice that this is a partial statement. I didn't write denotation of T equals denotation of simplified T, because total correctness does not hold. As I said, this simplifier is only performing syntactic transformations. So for example, 0 times set of booleans is simplified down to 0, but 0 times set of booleans doesn't have any denotation. So this is just an example. And the proof of this actually is still in progress, because so I did the most difficult cases, but it's actually very, very long to prove, because it's I think it's three nested inductions, and so I have like 300 or 400 cases to do, and they cannot be discharged automatically, so I have to write them down actually. And I think 4 cases are remaining. Like in total, I have 26 or 27 constructors, and 4 cases are remaining. Right.
This is only about the denotation.
This is only about the denotation. So yeah, for the contributions, of course, the encoding itself, so the tool here is my biggest contribution. But just the fact of defining formal semantics for the B language and the SMT-LIB language, it could be already on a separate project. And yeah, it's current work and also future work, the correctness of the encoding, and working on it full time.
Great, thank you very much. We have time for 1 or 2 questions before we all go to the coffee break. Yes.
Are substitutions part of your concrete syntax as it is done in the B book?
Not exactly as it's done in the B book. Actually, I'm not handling substitutions. So I cannot substitute term from the B syntax. It's not a constructor. Among my concrete constructors, I don't have substitution.
And I have a following question. Again, with respect to the B book, so the semantics of a B is defined with general substitution in the B book. So do you plan to align your denotational semantics with this formal semantics done by Gabriel?
So the simple answer is no. And so why? Because actually I'm not giving semantics to the B language. I'm giving semantics to B proof obligations. And so this is what I aligned. This is why I aligned the semantics on this subset, which is really a subset, a constrained subset of the B language. Because in proof obligations, everything is already kind of simplified, and everything, for example, substitutions and so on, they never appear in proof obligations.
Thanks.
Yes.
So you had to redefine math mostly to do what you want to do. And if you had to start over again, would you choose lean again, or do you?
Yeah. So I started things in Isabelle, but then the type system is not powerful enough to express what I want to express, but it's possible to do it. But the second reason is that I want a proof assistant that allows, that easily allows extraction. And with Isabelle, it's kind of a pain to extract code. And here there is actually no extraction. Lean is a programming language, so it's just compilation. So this is why I chose Lean. Then between Lean and Rock, for example, I'd say that I had to make a choice, and I chose Lean because it's more recent and so on. But yeah, between Lean and Rock, I mean, there's no real difference, apart from some differences in the type system and so on. But
Wonderful work I have seen here. One thing that reminds me the insertion of the syntactical objects into the domain reminds me about Herbrand universes, but Herbrand did it only for constants, not about the variables and terms with variables. So it looks to me it's a very good generalization of the Herbrand universes.
I think we have to go to the coffee break now before there is no coffee left. So as a reminder, yes, Sophie? As a reminder, if you are EPN funded, don't forget to sign the